Okay, so for this one, part 2 of 1.2, memory and storage. So we're going to look at the storage aspect of things now. So we're going to look a little bit closer at binary, and then we're going to look at how images and sound are stored and characters on your computer. So binary conversion, hopefully you can remember back to the days of binary. So if you're converting a number, you just need to make sure that you've got the numbers along the top. So you've got the 1, 2, 4, 8, hard with a mouse, 16, 32, 64, and 128. So every single exam question that asks you for binary, make sure you have got those numbers along the top. That will get you a working mark if it's worth 2 marks. And then all you've got to do then is stick in your numbers. So for instance, if I do this number here, you'll only ever get asked 8 bits. So now you work out that number. So we've got 128 plus 32 plus 16 plus 4 plus 1. Well, that's 21. 16 plus 4 is 20, and then plus 1. 32 and 128 is going to be 150. Add those two together, 171. So it's just about remembering those numbers along the top, and if you were converting it the other way, then just make sure that you go back to sticking in the numbers along there. If you can't remember what binary is, go back, have a look, revise it, make sure you know it. Hexadecimal, first thing I want you to do every time you get a hexadecimal question is write all of the numbers down. So 1 is 1, 2 is 2, and so forth up to 10. Once you get to 10, we can't represent 10 in a single bit. So the way that we do that, we do A. So then it's B, C, D, E, and you should have an F. Now, in an exam, you need to make sure you write them down, because I know so many people that do not get that right when they come to do it. And just a quick reminder, I don't want to go through this in too much detail on here, but essentially what you do is, if you've got, say for instance, let's go for 4F, and you're given that as a hexadecimal value, and you want to turn that into a binary number. Oh yeah. The way you do that, put F into 1, 2, 4, and 8 into a nibble. Same here for 4. So F is going to be 15, so that's all of them turned on. 4 is just going to be simply 4. So our binary number is 0, 0, 0, 1, 0, 0, 1, 1, 1, 1. Now if we want to turn that into denary, then we do that one 7. That's 16, 32, 64, 64 plus 7, which is 71. Okay, so 4F in denary is 71. If you're doing the other way around, you get 71, put it into binary, and then you write down what it is. So you've got 4, and you've got here 15. Oh, that's 15, that's 7. Muppet. 79. Apologies about that. So you've got the number into binary, and then you look at what the value is. So here you've got 15, here you've got 4, so it's 4F. Again, if you want more help with that, come and see your computing teacher or have a look. There's plenty of places for it. This is a recap. Then you've got binary addition, and the main things you need to know about my binary addition: if you're adding 0 and 0, you get 0. If you add a number on 1 or a 0, then you get a 1. If you do it the other way around, you also get a 1. If you're adding 2 1s together, you do a 0, carry the 1. And if you're adding 3 1s together, you do 1 carry the 1. So if you've got 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. Adding them together, we've got 0 plus 1 is 1, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1, 0 carry the 1, 0 plus 1 plus 1, 0 carry the 1, 1 plus 1 plus 1 is 1 carry the 1, 1 plus 1 plus 1, 1 carry the 1, 1 plus 1 plus 1, 1 carry the 1. What's this called? Called an overflow. I always say it, not been wrong yet. If there is a binary question where there's an addition on it, you're guaranteed that you get an overflow question for a 1 marker straight after, okay? Make sure you put your carry bits in, that's really important. You've then got character sets. Character sets, there are 2 main character sets you need to know, ASCII and Unicode. Essentially, character sets are just characters which a computer understands. Each of those characters will be given a binary number. So ASCII is essentially 8 bits. You do get away with saying 7 bits in an exam, but 8 bits can represent only 255 characters. Each character is given a unique binary value, and it does not contain characters from every single language, which makes it a little bit of a disadvantage there. If you want to make more characters, then you would use something called Unicode, or you can use extended ASCII. Unicode uses 16-bit, so it can represent many more characters actually, which allows you to do emojis in other languages, okay? Typical exam question there. Another exam question, what they might ask in character sets is, they might give you something like this, where L is 76, they might ask you what S is. So you'd have to work out the fact that P, Q, R, S. So Q would be 81, R would be 82, so S would be 83. And that could be an exam question right there as well. Not an awful lot you're going to get asked. Then you've got image representation, typical 2-3 mark question in an exam. 3 bullet points that I would remember, 3 things that will get you 3 marks. An image is made up of pixels. Each pixel can only have 1 colour, and each colour has a binary value. That will get you 3 marks nailed on in an exam all of the time, 100% of the time. Then you've got your colour depth. Colour depth is how many colours you can represent. The more bits you use to represent your colours is the more colours you can represent. So if you've got 1 bit, you've got the possibility of 0 or 1. That gives you 2 colours, so it can give you red and blue, for instance. If you had 2 bits, so 2 to the power of the number of bits, 2 bits, you have 4 colours. So you've got 0, 0, 0, 1, 1, 0, 1, 1. That's 4 possibilities, 4 different colours. If you had 8 bits, so 2 to the 8, 255, that would allow you to store 255 different colours. So just remember that. And then metadata. Metadata is data about data. That is a mark in an exam, data about data. And essentially what that means is all of the bits where you've got properties of your data. So things like the date that the file was saved, the name of the file, the extension, the resolution of it, the size of it in terms of the image width, the image height, anything along those lines. Oh, excuse me. Sound representation, 3 bullet points, remember, 3 marks in an exam. Your sound wave is sampled. The height of the wave, so the amplitude, is measured at set intervals, and each sample is represented using binary. Again, this is only a recap. If you really need to know a little bit more, ask your computer teacher, ask me, I can help. The bit depth that refers to your sound, the higher that bit depth, the clearer your sound will be. It'll be closer to the original. It's essentially a bit like the colour depth. The more you can store in, the more the bit depth you've got, then that will really increase the quality of your sound. So that's really key. And it comes back to that finding the storage size, so you can have a play around with that as you wish. And the last thing to think about before we go into the exam questions is some compression. So compression essentially makes the file size smaller. So if you want to send a file over the internet, then you would compress the file to make it smaller. 2 types, you've got lossless and lossy. I always remember it as you lose less data on lossless, so it doesn't remove data, so that means you can go back to the original. What it does is it rearranges it and orders it so that it's easier to get back to the original. Really good for text files, good for dictionary sort of compression, really good on that. Whereas lossy, it permanently loses data, permanently loses the quality, you can't ever go back. However, it's really good for sound and images because of some of that data you don't really need. And it does reduce it much more in terms of the size of the file, much more than lossless. So again, some exam questions we have to go at. The mark schemes on the slides after. Give me a pause as you go. If you want to do the questions and then you want one of us to mark it, happily do it. So do feel free to pop in and see us. So we're converting the denary number 221 into 8-bit binary, so have a go at that. So again, you have to show your working. So making sure that you've got the 1, the 2, the 4, the 8, the 16 and the 32, 64, 128 are there. Oh yeah. Oh. Shouldn't do that before I go to bed, should I? Record a video. Silly mistake. And then you get 1 mark for your answer. So you should have got 110, 11101. Then we're converting a hexadecimal number 2F and we're putting that into denary. Have a go at that. And again, you get a mark for working. So if you've done it the silly way of doing it, multiplying it by 16, blah, 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 that's fine. If you converted it into binary first and you've got 0, 0, 1, 0, 1, 1, 1, 1, ooh, yeah. Then you should have got 47. Convert the binary number into hexadecimal. So I've got that. And you have to get the correct mark. Now, I marked this exam paper and I remember it very well. A lot of people didn't put the 0 on the end. If you don't have the 0, you don't get the marks. So it's B0. If you only put B, you've lost a mark. This one's a character set question, so have a go at that. So again, on this one, make sure it's a capital T that you're putting because the lowercase t is a different value. So 83 we did in the example, so with the S, so T would be 84. And Unicode is a different one. You can be accepted there, extended ASCII, if you put it. So again, tick box, I like the tick boxes. Have a go at that. So which one can represent thousands of characters? Unicode. European characters, you can get in extended ASCII. Extended ASCII is only, I believe, 8 bits long, whereas ASCII is 7 bits long. But you can get away with saying that ASCII is 8 bits long. Confusing, I know. But Unicode will also be able to do that. And uses different character codes for uppercase and lowercase letters is all 3 of them. Metadata question, data about data. Have a go at that. So you could have a whole host of things: height, width, color depth, bit depth, date it was taken, geolocation, file size, file type, compression type, author, anything that's not on that list that is sensible, you'll have them all. Have them all. Binary, a bitmap image, and the reason why computers need data binary. So it goes back to those bullet points that I looked at in the slides earlier. So it's made up of pixels. Each pixel has a binary number. Each binary number has a color, and essentially you can only have one color in each pixel. That will get you 4 marks out of the 3. Second question, a bit harder, but you basically need it so that it only consists of logic gates and it has a power of either on or off. And it only basically has those options. More questions. So this one's a sound question. I think that was in last year or the year before, maybe. Question. Have a go. So again, it comes back to those bullet points that we looked at earlier. So your sound wave is sampled. The height or the amplitude is measured, and it's measured at set times. Now, if you'd have put that all on one line, you get 3 marks. That's how easy it is. So if you'd have just said the height of the wave is sampled at regular intervals, you would have got 3 marks. You would have got another mark for saying each sample is stored as a binary number. So plenty of marks to be getting there. Just remember those bullet points. It's just a memory test. Then the table. So duration changes from 10 minutes to 20. What happens? Well, your file size is going to increase, isn't it? You've gone from 10 minutes to 20. That's doubled into file size potentially. Your sample rate changes from 44 kilohertz to 8 kilohertz. Well, you're going down in less in terms of the sample rate, so you're sampling your amplitude at less time, so you're going to have less samples. That makes your file size smaller, but also decreases your accuracy as well. And your bit depth changes from 8 bits to 16 bits. Well, you're increasing, so you're increasing your file size and you're increasing your accuracy because it's better. And the last question is looking at compression. So you could have a mark for saying it reduces the file size, it takes less time to transmit or faster to download as you go through, and you could say that it requires less storage. Some people also put the fact that it uses less bandwidth, so it uses less data if you're downloading it on your phone. So some people managed to put that as well. So wondering if you got that. And why you would not use lossy on a text file? Well, it permanently loses data, which means that your text files then can't be compressed very well because you would lose data that you need. So hopefully, again, you're finding these useful. Let your computing teacher know if you need any help with any of it. But that is essentially the whole of 1.2 done in 2 videos. So if you know all of that information, all of those all that data, you will be absolutely fine for your exam for those 2 bits. Obviously, you've got 1.3, 1.4, 1.5, and 1.6 to do, but we'll get to those in a